Okay, so now we'll go on to start to talk about design. As, learning objectives. So you clearly ought to be able to define the failure mechanisms, because that's how we deal design, is try not to have failures. There's a bunch of assumptions, and you need to be able to understand the assumptions we're using when we analyze these walls. And then I'll go through the methods for computing earth pressures on cantilevered sheet pile walls, where we sand over sand or cohesionless over cohesionless soils, where you have a cohesionless soil over a clay soil, and where you have your clay over the clay soil. This is the first time we'll really talk about design of walls with clay soils behind her, because lots of times we're installing these in places as cut walls, and that's the material that's behind it, and we won't be able to do anything about it. And that, particularly if you're in a marine environment, it's real common to be in some marine environment where you've got clay soils, and you're going to have to install the wall into clay soils, and you're not going to get rid of them. So, that's the reason it's really important that you understand when to use short-term short-term undrained conditions and drained long-term analyses. So again, we're talking about cantilevered walls where there's no support. There's no support behind the wall. The sheet piles are just driven in, and they hold up the wall without any external support. So it's a cantilevered wall. So let's talk about the failure modes. Well, the first failure mode we'll talk about is the one we're not going to investigate, which is global stability. You can, by the way, if you're doing this if you're doing a design in like weak soils, you can actually just do this as a bearing capacity problem. You can just say, oh, well, this is my footing with this bearing stress in here. As at least a first order, you could do it just as a bearing capacity calculation. Don't even worry about trying to do a slope stability analysis. If you got a problem with that, then you need to do the slope stability type analysis. The other kind of failure that we can get is rigid rotation, where the wall just rotates to the point where it's beyond a usable state. And then the final failure we get, which is our structural failure, is if you exceed the section capacity of the sheet pile itself, and you form a plastic hinge. So those are the three failure modes, and we'll talk about the second two. All right, so our basic design procedure is we assume the wall rotates rigidly about some point O, and we're just going to design it so that we have a satisfactory factor of safety. And we actually don't usually do we don't necessarily do an analysis for movements. So if it does rotate about point O, then above point O, we should have active, on the back side of the wall, on the retained earth side of the wall, above O, we should have active conditions because the wall is moving away from then. But below the point O, we're going to have passive, because the wall is pushing into the soil there. And then on the front side of the wall, we're going to have exactly the opposite situation. Near the ground surface, or the mud line if you're under the water, there's going to be a passive zone, and below that there's going to be an active zone. So our assumptions in this are that the wall rotates rigidly, and I'm able to fully mobilize both the active and passive earth pressures. So we're going to start with our analysis for sands over sands. So if we're designing a wall in a cohesionless material, then C is equal to 0, phi is equal to phi prime. In spite of the fact that we said earlier that Coulomb's probably a slightly more accurate method, we generally use Rankine for these. There's not that much difference. These are very, very often installed in places where the horizontal ground surface is, where the ground surface is horizontal. So there's not a lot of, there wouldn't be a lot of back wall friction anyway. So let's look at the earth pressures. And to look at the earth pressures, it's helpful to draw some kind of envelopes on here. So all of our walls will have, we'll use the notation H is the height of the wall, just the free height of the wall above the mud line or the lower ground level. And D is the depth of the wall. This is generally the way people use the notation on there, but be careful when you're looking at design guides that that's how they do it. Occasionally you'll see some that define the height of the wall as the full height. But that's not very common. This is not common. The way we've shown it here is most common. Now if I draw a line down, if I draw a line from here that has a slope of 1 to gamma times kp, that's going to be the, if you want to think of that, it's kind of like the passive envelope. And it's going to intersect at the base of the wall. We're going to have this distance gamma h plus d times kp. I'm ignoring water right now. We'll talk about water later. And then I can do the same thing and draw an active envelope on the back side of the wall. And the length of that, the length from B to C on that one where it intersects that horizontal line at the base of the wall is going to be gamma times h plus d times ka. That should make sense. And we're going to need both these active and passive envelopes on the wall because we're going to have both active and passive pressures behind the wall, right? So we're going to need both of these envelopes. And then on the front side of the wall, we've got the same thing. We're going to have some passive envelope, and the intersection EB is going to be gamma times D times K passive, because D is the depth there. And similarly, we'll have an active envelope that goes from F to M, and that's going to have a length, projected length on the horizontal line there at the base of the wall of gamma times D times K active. So that should make sense. You understand what we're doing here? Yes? No? Maybe so. So we have these envelopes, and then if we know where O is, we can actually draw the earth pressure, we can actually draw the limit equilibrium earth pressures on each side of the wall. So above O, on the back side of the wall, we have active earth pressure, right? So that is going to follow the active line down, and that's going to be the earth pressure on the back side of the wall above O. And below O, whoops, I'm still doing above O. Above O, now on the front side of the wall, we're going to be following this passive envelope, right? We're going to be following the envelope that goes with K passive. So we're going to have an earth pressure diagram that looks like that. Obviously, this is going to be the passive force is going to be to the right, and the active force is going to be to the left. Now, what happens below O? Well, below O, behind the wall, I've got passive forces, right? So I'm going to get a trapezoidal resistance behind the wall that looks like this, where it goes out to the limit of the passive. I'm going to have this trapezoidal earth pressure below point O. And then on the front side of the wall, I'll have active pressure in that same case because the wall is moving away from it on the front side, and I'll have this trapezoidal area there. Now, all we got to do now is calculate the earth pressure, right? So, but we got a problem. There's something we don't know in this problem. Yeah, where is O? Exactly. So that's the whole trick. So we're going to use statics to help us find where O is. So there's some tricks to doing this. So this is the same envelope. I'm just putting it on a new page so I can draw on it. So if we think about this for a second, from A down to F prime here, we know we're going to be following the active envelope. And then after that, what you can think of is we're going to be subtracting this passive pressure from the active pressure we have behind the wall. So we're going to be following a line here from F to prime to E prime that's parallel to this line from F to E. So that's what's happening from the top. Well, what's the net earth pressure at the base of the wall? That's pretty simple. I've got this much pressure acting to the left, and I got this much acting to the right. So the net earth pressure at the base is going to start at some point J, which is going to be gamma dk, same distance as this, left of k. And these functions are all linear, so when we add them all together, we got to get a linear function, so we know it's a line. So I've got some line, my net earth pressure envelope is going to be coming down here, coming down some line here, and then coming back over here down some line. And so the things I know about it is, I know it's got to intersect at that point. I know it has to intersect at that point. I know the slope of this. And I don't know O, so I don't know Z. I don't actually know where this point G is. But I'm going to have a net earth pressure envelope that looks like that in brown, where this is going to be acting to the left, this section is going to be acting to the right, and this section is going to be acting to the left again. And so all I need to do is find the height Z, and I can draw my earth pressure envelope. We good? Jack? Okay. Same figure, cleaned up. So let's calculate some of these points we need to know. Well, this distance from B to J has got to be HD plus KP, the HD plus P, the passive distance, right, this whole distance here, minus this distance, right, so it's going to be gamma times H plus D K passive minus gamma D plus K active. This distance from F prime to E prime has got to be gamma times D times K passive minus gamma times H plus D times K active. So that's going to be that distance. And so I can think of this, if I want to, as adding up I can take three different triangular sections and add them together. So I can take this triangle, which is going to be my active earth pressure. I'm going to sort of do like a superposition problem here. I'm going to take this one that's acting in this direction. And then I'm going to subtract from it this triangle, E prime, F prime, C prime, that acts in this direction. And then I'm going to add back in the other direction this triangle, E prime, G, J, acting in this direction. And when I do that, I'll get my net. I'll get this net brown triangle, if you can see that. So I'm taking ABC. So if you want to think about this, I'm actually going to call this minus. If I call this X, oops. I call this X, call this Y. This will be negative. Then I'm going to take this whole triangle here. Let me do some erasing here. I'm going to call this X, I'm going to call this Y. So this one's going to be positive. This one's going to be negative. right? So now what I'm left with is negative stresses. I've eliminated this part of that triangle, but now I have negative stresses over here. This part here will actually be 0 now. And so I'm going to add in this one positive back, and that'll leave me the net of this plus this plus this. So that'll be the net earth pressure acting I have when I'm done. Did you follow that? Yes, no, maybe so. All right, so graphically what I'm going to do, I'm going to say that this net earth pressure diagram is going to be equal to A minus ABC, because that's acting in the minus x direction, right? Plus E prime F prime C, because that block is acting in the positive x direction, minus E prime GJ, which is again acting in the negative x direction. So that's my net earth pressure diagram. So what I want to do is I want to find Z such that the sum of the horizontal forces is equal to 0, right? So the sum of the horizontal forces is going to be 0. Well, the area of the triangle, this is the area of the triangle ABC. Right, the base was gamma, it's going to be 1/2 gamma h plus d squared times Ka, because the length of the base, if you remember, go back, the length of the base of that was gamma h plus d, right, and the height of that triangle is hd, so the area of that triangle is hd squared times gamma times Ka 1/2. Got it? Yes, no? So the area of E prime F prime C is gamma d squared Kp. I'm not going to go through that one, but you can prove to yourself that that's right. And then the area of E prime GJ is, again, it's minus because it's acting in a negative x direction, 1/2 gamma Z H minus 2D times Kp minus Ka. So I can write that in terms, so Z appears in my equation right here because I had to assume the height of Z. So I can write the equation in terms of Z, and it gives me this equation. So I know Z now, right? So think about whether or not we think about whether or not we can actually calculate Z right now. And as soon as everybody's caught up, we'll step back a minute. All right, let's go back to our very first slide. All right, so here's a cantilevered retaining wall that we want to design. What do we need to do to design this? What do we need to determine? What do we know before we start the design? What's the client tell us? What's the owner telling us? Yeah, we know this. The owner says, hey, I want this much clear space here, right? What is it we act? There's two things. There's really only two things we have to do to design this wall. We've got to determine D, right? That's one of our design goals, because we don't know that. We got to know how deep to drive it. We don't want it to fall over. And then what's the other thing that we need to know? But once we figured out D, there's one more thing we need to design. That we need to pick a cross section that has a modulus to carry the loads without yielding, right? So there's two things that so our goals in this are to determine D and the section modulus. So let's go back to my equation. So here we are. Do we know Z? No, we don't know Z. We don't know D. We don't know we don't know D and Z, right? And if we knew D, we could calculate Z, but this is the Z that's going to give us 0. So we don't know the answer to this question. We've got two unknowns and only one equation. We don't know Z and we don't know D. So we need another equation. So we're going to use moment equilibrium for our second equation. So we're going to sum moments about the base. And this should look a lot like what we just did. So I'm going to take the areas of those triangles and multiply by the lever arms. And I'm not going to derive this one for you. You should go home and derive it yourself. But here's the first. We'll look at the first one. This was the area of our triangle, right? And that triangle had a height above the ground surface of, oops. That was the triangle AB, that's this triangle. Right? So the height of so the force is acting there, and this lever arm is going to be 1/3 of H plus D. Right? So where's my moment equation? So here's my moment equation. So it's 1/3. This is the earth pressure, and this is X, the moment arm. Similarly, the second one, this was our total earth pressure. The height of the second one is D, right? So that one acts at D over 3. All right, there's X bar. And our third one, this was P. And that one has a height, you can't see it anymore because I covered it up, but this was Z, right? Was the height of that one? So its moment arm, X bar, is Z over 3. So now I'm in good shape. I can simplify this a little bit. It's convenient to put it in this form, and you notice that you got Z squared in this equation, and you got D cubed. So now I have two equations and two unknowns for D and Z, but they're not particularly, so I need to find D and Z, but you got a cubic in D and you got a squared function in Z. So the easiest way to do it is to use an iterative solution. So what we usually do is we pick a D, and the easiest way to do this is pick a D. There's some guidance. This comes from the 99 FHWA manual. By the way, I originally thought I'd completely replaced the 99 FHWA manual with the 2007 one, and then I went when I went over this section, I went to find the new sections for the sheet piles in there. And there's a bunch of stuff in the 99 one that's not in the 2007 one, so I loaded that up for you. And I gave you two other, did I give you two other sheet pile design manuals? I gave you the Corps of Engineers one, and I gave you USS Steel one and two, I think. And they all those have these solutions derived in them for you, or at least presented, maybe not derived. So you can use any one of those. But you need some place to start your iteration. So this is a good guidance that you can use. And it's based on the N60 SPT value for the sands. So you're going to pick one of those. And we're going to use our first equation. Remember, equation 1 was, whoops, I lost it. So equation 1, we'd solve for z. So we're going to pick a d, calculate z. And then we'll take z from this step, and we'll put that in equation 2. Right? This is equation 2. So we'll stick our d in there, and it won't be equal to 0, right? We've assumed d, we got z, we're going to stick it in there, it's not going to be equal to 0. And so then we'll just make an adjustment. But then we'll change d, and we'll repeat this whole process until we get closure. So you can do this with a spreadsheet in 5 or 6 iterations or a few seconds, so it's pretty easy to do. And you'll get to do it for your next design problem. So that's relatively easy to do, and I think this is the right place for a break. What are we doing next? Yeah, this is a great place for a break. So we'll take a break here and finish this up afterwards. Okay, so we've been talking about sand over sand. We've gotten through the basic design method for that, and we're going to talk a little bit now about factors of safety and how we deal with this in ASD. So there's different approaches to ensuring an acceptable design, and as far as I know, there's no universally accepted approach. On the ASD side, there's two basic methods for doing this. Now, I'll point out that this guidance comes from the 99 NHI, and if you look at the 2007 one, they'll give you the LRFD design method, the geotechnical LRFD design methodology for you. And as I said, if we get a chance, if we have time, we'll spend some time looking at LRFD methods. But at the moment, I'm not prepared to do that. So there's the first approach, and FHWA is not the only one that does this, but it's presented in that 99 manual, is when you finish your design, realize now we've designed this, we've created a design that is stable in equilibrium, so we need some factor of safety. You ensure your safety by increasing the depth. So you do all your calculations with unfactored loads. And once you got your D, then you say, okay, my design, that's my static D, and my design D will be 20 to 40% more than that. And if you do like a slope stability kind of analysis on it, you'll find that gives you a factor of safety on loads someplace between 1.5 to 2. It depends on how you do the assumptions. The other method is to reduce KP by a factor of 1.5 to 2, and then just use your K active. So you just, before you start your calculations, take KP and reduce that by a factor of safety of 1.5 to 2, and then just do your calculations, and the D you get. And these two methods should give you comparable answers. So the first philosophy is, well, I got D, once I'm done with that, I'm just going to drive it deeper and I should be safer. The second one is, well, it's the passive earth pressure that's providing the resistance, and I'll factor the passive earth pressure. And realize that's not really true, because on one side of the wall you got you got active and passive on both sides of the wall, but predominantly your resistance is going to be coming from passive earth pressure. So I'm going to factor the passive earth pressure and take the design from that. The Corps of Engineers presents another method, a completely different approach to it. And again, these aren't the only people who do it, but I'm showing you where it's presented. So in this one, what you do is factor the shear strength of the soil. So you're going to have, you're going to use a tan, and you're not factoring phi, you're factoring tan phi. You factor tan phi by the factor of safety, and what you do is you're going to get an effective factor of safety from that, and then you factor C, so that I have to look this up. I think this is right now. I'm looking at this right now, and I'm trying to remember if this formula is right, or if what you're doing is tan phi divided by F. I'm going to put a question mark there, and I'll look it up, and I'll get back to you. I'm pretty sure the formula I've got is correct. So you're picking a phi that gives you a tangent of phi equal to the tangent. You're picking a phi that such that tan of your effective phi gives you tan of phi over F. So you're actually factoring the strength and not the friction angle. And then you see your effective C is C over the factor of safety. And they recommend applying this factor of safety only, again, to computing the passive. So it's similar to this method, but a slightly different approach. And it makes sense then you're not going to factor if you consider the active to be your driving force, you're not going to put a factor of safety on the active, you're going to put it on the passive side. And they give some guidance on how to select factors of safety, and they recommend factors of safety of 1.1 to 1.5, depending on what your soil conditions are and also what your wall function is. So one of the nice things about the Corps of Engineers manual is they give you some guidance about selecting factors of safety based on function. And you can find that in table 5.1 of that engineering manual. So those are two completely different approaches. There's almost 3 different approaches in there, depending on how you want to look at it. And as far as I know, they're all used. And so if you're doing these for agencies, you need to check out what your agency says is the right way to do it. And then there's another way to do it. If you're doing anything for any FHWA projects, then you're going to have to be using the LRFD design methods, which, again, we were not ready to talk about at this time. I think if people can get away with it, what they most commonly do is do this increasing the depth by 20 to 40% because it's really, really easy. You just do your calculation and you're done, say, okay, 20% deeper, away we go. It's really, really common. In fact, I think it's especially common in temporary shoring to do it that way. That it's really easy. Okay. All right, let's talk about how we deal with groundwater. So if the water is present, it's really common when you're doing these in marine environments. You essentially have the groundwater table is horizontal on both sides of the wall. In which case, all you got to do is do all your calculations with the buoyant unit weight of the soil, and then add the water pressures back in afterwards. So you have to decide if you've got water always on the left-hand side or not, because if the water is going to be the same on both sides, then it's actually always going to balance out, and it's basically not going to be there. But if this side is going to draw down or something, not only you might have this, but you also might have flow, which you have to worry about it. So you need to worry about all those situations. But you're going to have your active envelope on this side is going to be D plus H times gamma prime, and on your passive on this side is going to be D times gamma prime times Kp. And so when you go back to draw these envelopes, really all you're going to do is you're going to come in here and put gamma primes in here. Right? That's essentially all you're doing. And then, in this case, this is not the solution. I was just doing an illustrative solution there. You're going to have gamma water on both sides. Now, in this case, the two gamma waters are going to cancel each other out. But that's not always the case. So if you're in a marine environment, lots of times you have tidal fluctuations. And you can have significant tidal fluctuations, which means this side is going to drop fairly quickly. But that's not going to be the case on the back side of the wall. So it's really important in tidal environments that you understand, in a marine environment, you understand the tide conditions you can get there, particularly if you're doing a permanent wall. And the safest assumption to assume is that you put the high tide water table, or maybe even the water table at the ground surface, because there could be infiltration and there could be precipitation. And anyway, you pick a high water table on the fill side of the wall, and then figure out what your lowest tide possibility is and put that on the other side, and then you're going to have imbalanced water pressures. So it's pretty straightforward. So that's what this is showing. And then if you have a permanent difference on both sides, you need to draw a flow net, and you need to use the water pressures that are actually going to be generated from the flow conditions. So, yes? Yeah. Sorry. If I forget that we have non-geotechs in here and I'm making too many assumptions, please ask like that. Yes. So your buoyant unit weight is just the unit weight of water minus gamma, the unit weight of your soil, the saturated unit weight of your soil minus gamma water. Thanks for asking. So it's pretty. So the calculations are pretty simple. This is actually the thing that you need to really worry about. You know, what are the real water? You know, what's the real hydraulic condition in there? So in the second case, notice that you've got different water pressure on both sides, and they're not going to cancel out, and you're going to end up with a water pressure on the right-hand side that looks like this. Right? That's a substantially different situation than you had in the other case. No, that's just a gamma. I thought my gamma looked like a 2, so I was trying to make it look more like a gamma. And I didn't connect the little thing to the other side, so it looked like a prime. Gamma prime is saturated gamma of your soil minus gamma water. Boy, that's the most feedback I got in class, how to make mistakes more often. Okay? Okay, well, let's talk about what happens with clay soils. So early in the quarter, we said, you know, don't design walls with clay behind them. Well, if you're going to go if you're going to install a wall, you know, in some marine environment that's got clay, there's nothing you can do about it. So you got to know how to deal with clay soils here. So it's important that you consider both the short-term and long-term conditions in this case. So we can use a phi equals 0 condition for the short term, and in the long term we'll have to use drain conditions. So in the short term, our strength is going to be equal to the undrained strength, which is just equal to the unconfined compression strength divided by 2. K active is going to be equal to K passive is going to be equal to 1, so our earth pressure calculations are a little easier, right? Because we're under phi equals 0 conditions here. Under long-term conditions, our phi will be whatever our drain friction angle is. Generally speaking, well, I don't say generally speaking. Often we can ignore, in these marine environments, you've got these normally consolidated soils. It's very, they're very, very common for them to be normally consolidated, in which cases you can assume C is equal to 0. So in that case, the long-term condition just looks like the condition we just did for cohesionless soils, because you basically have a cohesionless, normally consolidated clay. You just got to use the internal friction angle of the clay. So that looks like the example we just did. And that's actually really common to do, because lots of times when you're doing these things in clays, it's in a marine environment and the soils are normally consolidated. So let's talk about the undrained phi equals 0 analysis then. So in this case, I've got a clay soil over a clay soil. I've got phi equals 0 conditions in both. I could have different undrained shear strengths in them. I think I do this example with a single undrained shear strength, but you can do it with 2. It's not that hard. So my earth pressure diagram is going to look something like this. Remember, for the active earth pressure is going to be negative 2 times the cohesion. Remember that when we have remember that our horizontal earth pressure is going to be equal to Ka times sigma z in the case for the active minus 2c times the minus 2c times the square root of Ka. Well, this is all, the k's are equal to 1 in this case. And so sigma x is just equal to sigma z minus 2c. Well, at the ground surface, you have no vertical stress. So your earth pressure diagram of the ground surface actually looks like this. And then it's going to increase. It's just gamma times h, because Ka is equal to 1. So that's your active, that's your active earth pressure envelope on the back side of the wall. And the intersection right here is going to be gamma h minus 2 times SU, right? Because the vertical stress there is going to be gamma h, so that's going to be gamma h minus 2 times SU. It's going to be important in just a second. And the intercept at the bottom is going to be gamma times h plus d minus 2 times SU. Now, there's no difference between active and passive here, so I don't have to have an active envelope and a passive envelope because I've only got one case, right? Because Ka is equal to Kp. The depth to the place where there's 0, we went over this when we were talking about earth pressure, is going to be 2 times SU divided by gamma of your soil. That's going to be important. And then on the passive side, this slope is still gamma times h. And that the length along the base there is going to be gamma times d plus 2 SU, because this distance right here is 2 SU. So what's my net earth pressure diagram? Well, my net earth pressure diagram, right, I've got 2 SU here and 2 SU there. This triangle and this triangle cancel each other out. We're going to ignore the negative earth pressure at the top because we're pretty sure the soil's not going to suck the wall back. Right? We're going to get a tension crack there. So we'll ignore that. If you got water up there, you should put the water pressure in. I may have left that off in this one. I'll show you in a second. And so we're going to have this net earth pressure. All we're going to have is this triangle there, and we're going to have 4 SU minus gamma h at the base. You should assume that you're going to get a tension crack here, and you should add in this value, where this is going to be gamma water times Z. So at the base, it will be gamma water over gamma times 2 SU. Because you should assume you're going to get a tension crack there right behind the wall. It's going to fill with water. If you have water on this side, that's going to go away. But if you don't, but if it's drawn down, it's not. So those are, what are the net forces when the wall is moving to the right? Well, when the wall moves to the right, so I'm not sure I said this clearly. These are the net forces when the wall moves to the left, right? I haven't looked. I'm not searching for the point of rotation yet. I'm just giving you the net forces when the wall moves to the left, right? Are you with me? What are the net forces when the wall moves to the right? Well, when the wall moves to the right, I have plus 2SU at the surface. This is still going to increase as gamma H, right? Because Ka is Kp is equal to 1. At this point, I'm going to have 2 times gamma plus 2SU. Sorry, gamma H plus 2SU. And then I'm going to start having my earth pressure on the other side. That's going to also increase as gamma H. And so this distance from here to here, which is going to be the contribution from the soil on the left, excuse me, is going to be gamma D minus 2SU. Sorry. Gamma D minus 2SU, because I'm going to start minus 2SU over in this direction. So my net pressure when my net pressure acting here is just going to be gamma H plus 4SU. Right, because I'm going to take this diagram and I'm going to add it to, let me do it the other way, sorry. I'm going to take that diagram, I'm going to add it to this diagram, and the net pressure I'm going to get acting on the wall is just gamma H plus 4SU. So an interesting little solution. So I've got this solution plus that solution. I have to find my point of rotation. So now I'm back to the same problem. I got to find O. But the solution's a lot easier because I've got these functions that are both fixed, right? This is gamma H plus 2SU, and this is 2SU. I think that's right. Let me double check. Go back far enough. Oh, I'm sorry, 4SU minus gamma H. I knew that something was wrong with that. This is 4SU minus gamma H. Is that gamma H plus 2 or gamma H plus 4 now? I don't remember. Gamma H plus 4SU. So this is my net earth pressure diagram. This part's not going to change. The depth of that's 2SU over gamma. The value of that is gamma H minus SU. The value here is 4SU minus gamma H, and the value down here is gamma H plus 4SU. And all we need to do now is find O. And this one, there's a closed form solution for O, I believe. I forgot to look at that before I came today. So it's a lot simpler when you have phi equals 0 conditions. It's a little strange how you get there because the active is equal to the passive, but it's a lot simpler diagram. Okay, well, what happens if we have a sand fill over clay base? This is really common. You've got a clay material in your harbor, you drive your sheet pile, and then you put a hydraulic sand fill on top of it. That's a very, very common setup. So on the surface, you've got sand, right? So we've got sand, we're going to have phi sand, C is equal to 0. And at the base, we're going to use phi equals 0 conditions, and we have phi equals 0, and the strength is equal to SU. Well, this is actually pretty simple. If you think about it, what we have going on here is you're going to have your active earth pressure above the base, above the mud line, and it's just going to be H times the buoyant unit weight of the sand, H times buoyant unit weight of the sands times your K active. And then if you think about the sand is just providing a surcharge load onto the clay layer, all we have now is we just have just a clay layer. If you want to think about this, if you can imagine all this going away, and all you have is this clay layer, all you have is this surcharge load, gamma times H prime acting on top of the clay layer. So if you do that, then this block is going to be SU minus H times gamma prime, and this block at the bottom is going to be 4SU plus H times gamma prime sand. And then don't forget, if we're doing a drain analysis on the sand, we have to add the water back in. But we've got water on this side and we've got water on that side, and these two cancel each other out. Now we're assuming they cancel each other out, so we're back to the same situation. If you do have a difference in the height of the water on the two sides, that you need to account for that, because we're assuming that it's the same on both sides and they cancel out. So you should go, if you don't, you probably don't all have a 100% grasp on how these were derived, so you should go back and either through the lecture or the notes, or go back and read either the 99 FHWA manual, or the Corps of Engineers manual, or the steel pile manual that I gave you. All have these derivations in them, and you can go through those and make sure you understand those. All right, so let's talk about structural design real quickly, and we'll be done. So once we're done, once we've got our earth pressure diagram, it's pretty simple then to compute the moment based on the earth pressure diagram that we get. And then once you got that, all you're going to do is go select a steel design. All you're going to do is you're going to use AISC methods to select your sheet pile, and basically all you're doing is you're selecting your section modulus. Now a lot of times these are done, these designs are done with allowable stress design, which is still a legal way to do steel design if you want to. And I think people do it that way because it's really simple and it's easier, and you've already done all the earth pressure calculations with unfactored loads. So all you got to do is go in there and make sure that you have, if you've got other loads, you got to make sure you have those in there, and then you just do your ASD design for your sheet pile wall. I'm sure some people are doing it with LRFD design, in which case you'd have to factor your loads appropriately. It's kind of hard to do that though, because you got water loads separate from earth pressure loads, and they all have different load factors, and so it's really common for people to use allowable stress design for this. Whoops. So that part's pretty simple, and the design problem I give you, I'll ask you to go through and find the appropriate section for the design. So there's a couple things we didn't talk about that are, well, let's talk about assumptions quickly. So what are some of the assumptions? There's a real important implicit assumption in these design methods that we haven't talked about. We talked about a lot in, it's a situation that we talked a lot about in gravity walls, but we didn't even bat an eye about it here, and it has to do with the active and passive pressure. What's a real implicit assumption here that about active and passive we haven't talked about? Well, we are generally using Rankine and ignoring wall friction. That's correct. If you want to, you can use a Coulomb analysis and put in wall friction. Besides the magnitude of the active and the passive pressure, what's the other big difference between the two? Displacement required to mobilize them. And remember, particularly when I'll go back to the sand example because it's drained analysis. So we get our net earth pressure diagram here. We're assuming that we're mobilizing full active and full passive on both sides of the wall. And we're not saying anything about movement. I think there's two reasons this works. One is you actually do get quite a bit of movement in these walls when you design them, particularly if you're doing them in an environment where you're filling behind a marine environment. So you could actually get quite a bit of displacement and still be an acceptable design, so long as when you're done at the end of it, you didn't have too much displacement. So I think that's one reason that it seems to work okay. And then the other one is if you're doing the exercise where what you're doing is you're putting your factor of safety on the passive earth pressure. What you're really saying, one way to think about that is what I'm really saying is, well, I'm not going to mobilize all the for a ultimate failure mode. I've got the rest of that passive displacement to keep me from having a catastrophic failure. I may get large displacements, but at least I won't have an ultimate failure that way. But that's an implicit assumption to all these ones, is that we're mobilizing both the active and the passive together. And obviously the wall is rotating. You can't have the same displacements everywhere. So, okay. Boy, it's one other thing I was going to cover, and I can't remember what it was. Oh well. Questions? Everybody happy? All right. I have nothing else for you today.